Welcome back, everyone. A major shift is underway in the world of computing as neuromorphic chips begin to show promise in replacing traditional graphics processing units for artificial intelligence applications. Neuromorphic chips are designed to mimic the structure and function of the human brain, using networks of artificial neurons and synapses that can process information in parallel and adapt over time. This architecture allows for faster computation and significantly lower power consumption when compared to standard processors. Companies and research institutions are now testing these chips in a range of AI tasks, from image recognition to autonomous navigation. Early results suggest that neuromorphic systems can handle certain workloads more efficiently and with greater flexibility than GPUs, especially in edge computing environments where space and energy are limited. As development accelerates, these brain-inspired processors could become the foundation of next-generation AI platforms that operate more like biological systems than traditional machines. Neuromorphic chips operate by replicating how biological neurons and synapses transmit signals. At the core of these chips are electronic components called spiking neurons. Unlike traditional processors that operate in linear sequences, neuromorphic systems transmit signals in pulses or spikes, similar to the way neurons fire in the brain. Each artificial neuron only activates when it receives a sufficient signal, reducing unnecessary computation and saving power. These spikes travel through an interconnected web of synthetic synapses, where the strength of the connection can vary based on usage. This variability allows the system to learn by adjusting the weight of each connection in response to patterns in the input data. The physical design of neuromorphic chips is fundamentally different from conventional CPUs and GPUs. Traditional processors separate memory and computation into distinct units, which creates a bottleneck as data constantly moves back and forth. In neuromorphic chips, memory and processing are co-located within each artificial neuron, enabling much faster and more efficient data handling. This architecture, known as in-memory computing, allows for parallel processing on a massive scale. The reduced need for data shuttling also lowers energy consumption and heat generation, making neuromorphic chips highly suitable for embedded systems and real-time processing. Learning in neuromorphic systems often uses a model called spike timing dependent plasticity. This method mimics how the timing between neuron spikes in biological systems affects the strength of their connections. If one neuron consistently fires shortly before another, the connection between them is strengthened. If the timing is reversed or inconsistent, the connection weakens. This allows the system to form memories and learn patterns without external supervision. Such self-organizing behavior is particularly useful in tasks like anomaly detection, sensor fusion, and robotics, where conditions change rapidly and adaptability is crucial. To handle complex tasks, neuromorphic chips rely on networks of thousands or even millions of artificial neurons. These networks are arranged in layers or clusters, with each group handling a specific part of the task. Some layers might process raw input data such as audio or video signals, while others identify patterns or make decisions. Communication between layers is handled by a routing fabric that mimics the connectivity of the brain. This structure allows for modular and scalable systems that can be tailored to different applications without needing to redesign the entire chip. Programming a neuromorphic chip involves defining the architecture of the neuron network and setting the rules for learning and adaptation. Developers use specialized software tools to map data inputs and outputs to the spiking neuron model. Training often happens in real time, with the system exposed to repeated examples until it develops accurate associations. Because the chips are event-driven, they only process information when meaningful changes occur in the input data, which dramatically improves efficiency. This event-based approach is ideal for applications like surveillance, where constant monitoring is needed, but most of the data is not important. Sensory integration is another strength of neuromorphic systems. These chips can process data from multiple sources simultaneously, including visual, auditory, and tactile inputs. In a robotic platform, for instance, neuromorphic processors could help combine camera feeds, microphone inputs, and touch sensor data into a coherent understanding of the environment. This mirrors the human ability to perceive and react to complex situations, using multiple senses. Because the processors work in parallel and adaptively, they can respond in near real time without the delays typical of centralized systems. Neuromorphic chips also include mechanisms for fault tolerance and self-repair. Inspired by biological redundancy, many neuromorphic systems are designed to reroute signals automatically if certain neurons or synapses fail. This allows the system to continue functioning even when some hardware components are damaged or degraded. Such resilience is important for mission-critical applications such as aerospace or autonomous vehicles, where hardware failure can be catastrophic. It also extends the operational lifespan of devices in the field, reducing maintenance needs and increasing reliability. Energy efficiency is a major advantage of neuromorphic technology. Because neurons only activate when necessary and computation occurs locally, these chips consume just a fraction of the power required by conventional processors. This makes them ideal for battery-powered devices and remote sensors that must operate for extended periods without human intervention. In edge computing environments where devices must process data locally due to bandwidth or latency constraints, neuromorphic chips can provide high performance with minimal energy draw. Some prototypes have even demonstrated useful AI functionality using only milliwatts of power. Deployment of neuromorphic chips often involves integration with other computing systems. While neuromorphic processors are excellent at specific tasks like pattern recognition and real-time response, they may be paired with general-purpose processors for broader control and interface functions. In such configurations, the neuromorphic chip acts as a co-processor, handling tasks like audio processing, sensor monitoring, or anomaly detection. This hybrid setup allows developers to take advantage of neuromorphic efficiency while retaining compatibility with existing software stacks and communication protocols. As software tools mature, more complex and autonomous systems will be able to fully utilize neuromorphic hardware in integrated environments. Looking ahead, neuromorphic chips could become the backbone of truly autonomous systems that learn and adapt without centralized training. As hardware continues to improve, future versions may feature billions of artificial neurons capable of real-time interaction with the environment, learning from raw experience much like a biological brain. This could lead to highly capable service robots, adaptive control systems in factories, or even intelligent prosthetics that respond to user intent without predefined commands. Coupled with advances in flexible electronics and miniaturization, neuromorphic computing might power wearable cognitive assistants or implantable devices that enhance human perception and decision-making in real time. If neuromorphic chips continue their current trajectory of improvement, they could soon become standard components in everything from mobile devices to advanced robotics. These chips would enable systems that learn continuously, process sensory data in real time, and adapt dynamically to changing environments without relying on cloud computing infrastructure. Such capabilities could revolutionize fields like autonomous transportation, personalized healthcare, and real-time security analysis. Moreover, the energy efficiency of neuromorphic hardware makes it ideal for off-grid or wearable applications where battery life is critical. As fabrication processes improve and support software becomes more robust, the transition from GPU-based AI to neuromorphic systems may become inevitable. This shift would not only improve performance, but also bring artificial intelligence closer to the way human cognition naturally functions. Thank you very much for watching. Please like and subscribe.